An overlay.
We're live.
Are we? Oh, we are.
I'm really not sure. I'm really not sure.
This is the day.
We're sort of live. We're semi-live.
100% not sure if we're live. Alive? One of those things.
Alive.
Cheers.
Cheers.
Cheers. Good to see you both.
Yeah, you too. Ooh. Oh, that's pretty good.
What you drinking there, Barb?
I am drinking, I've never had this before, Angry Orchard Peach Mango hard cider.
Ooh. We are mango twins. I'm
Nice.
drinking Mango Cardigan because it's the old standard for our household, it seems.
That's good.
How about you, Miss Carlin Ma?
I am drinking lemon blackberry kombucha made by a friend of ours.
Ooh.
Yes, very ooh. I'm adding a little lime to it because it's a bit sweet still. It's in its second ferment. Hold on, I have the ABV. Hold on. Blah blah blah.
Blah, blah, blah.
It is.
Ha, ha, ha.
Let's see, I meant to. 1.366 ABV.
1.7 gigawatts.
Yeah, it's the one that was tested. She works for a brewery, so she had it tested. 1.36. So it has an inordinate effect on me for some reason. The kombuchas. So I'm sure I'll be glowy again. But it's really good with the addition of a lime twist, so to say.
Very good.
That sounds nice.
Homemade hooch, man. That's like extra level.
Yeah.
Yeah, really is.
Yeah.
You're for reals, Carlin Ma.
It's for reals. She made another one that has basil in it, and like it's. I mean, this is not me. I still have our water kefir greens. I could do that again at our maybe in a couple weeks. Yeah, she made one with basil in it too. That is so good. But the lime is bringing it to this party.
Bringing it to this party.
Oh yeah, what is this party? This is called Deep Fried Neurons.
Oh yeah. We have a catchphrase, and this is it.
No, I didn't make this an agenda again.
The agenda has all of the options on it, and I always forget them. And then I click over really fast, and I go, "Oh, that's good."
Well, I'm so sorry. I have failed you all.
That's okay. I had to rouse Carlin from her nap earlier.
Yeah, hard nap.
I was sprinting out, or I was trying to sprint out the door at work. But we have camp starting on Monday. And we're not. We got to do more over the weekend. And I'm trying to get out the door, and people are like, "Oh, Barb! Oh, Barb! Oh, Barb!"
By the way, Barb.
I have to leave now. Wait, there's a thing happening here tomorrow. We have to be ready for that.
Dough.
What are you drinking? Oh, you're drinking Mango Cart. Sorry.
Mango Cart. I got double Mango Cart since I'm the one presenting today.
I know. It's exciting.
It's very exciting.
It's extremely.
We'll see. We'll see if it all goes up in flames.
Exciting.
This might be the episode that creates a huge crater in Southern California.
Please.
We shall see.
Perfect. I'm on board.
We have an agenda.
I think I might be supplementing my drink.
Agenda? What?
I might be supplementing my drink for updates on this with peanuts.
Uh-oh.
So I don't kill my stomach, And it's happy hour.
Yes, you always gotta have the snacks. This is the one of the best rules of life that Hitchhiker's Guide to the Galaxy taught me, was to always have little snacks in your bag just in case, because having a little bit of protein keeps you from your ectoplasm from coming outside of your body when you transdimensionally portal.
It's important.
Very important.
You do not want that ectoplasm all over the place. It's just bad etiquette.
Yeah.
Bad etiquette.
It's hard to mop up. It sticks to the sponge.
Oh, here we go. Deep fried neurons. Friday. The hell with all the rest. The hell with all the rest. I messed it up even.
Always carry a towel.
Always carry a towel. That's our catchphrase. Where's your towel? I don't have a towel. This is a problem. Well, not here.
Well, just wait till you spill your drink. Then you'll be wanting a towel.
I probably have fabric. Oh, actually, wait.
Hey, there you go.
Oh, nice.
Perfect. Shop towel for the win.
This was the towel that I got damp and had on hand for when I was practicing setting steel wool on fire earlier this week, as you do.
As you do.
As you do.
You know, things Barb does during the week.
Sounds like a good week.
It was a week. It had certainly been a week.
Tell us about your thanks for existing.
Was that aimed at me?
Sure.
I can go.
Yes.
I don't know.
It was definitely aimed at you.
I think I was the last one who talked. So
yes, it was definitely aimed at you, but it could have not been if you didn't want it to be.
Oh, I'm ready. I'm
Okay,
ready. I sprinted right before we went live to get my thanks for existing. My thanks for existing is these alcohol ink pens. Oh, which I just like the name. Oh, yeah.
Awesome.
So, like, I have a lot of water-based pens, which are like brush pens, so you can do interesting, multi-depth, multi-width lines. But now I got these, which have a chisel tip and
that's good.
a brush tip.
Oh yeah, I love those style. Yeah.
And the interesting thing for those who don't know about alcohol pens, like they work a little bit differently than like water-based markers, water-based art markers. One of the ways is that it blends a little bit more easily. Water-based markers more often kind of do like an overlap. And you can see kind of the lines. For instance, this, and I don't know if you can see it. Here, wait, let me go full.
Okay, so you can sort of blend up the color more.
Come on, full screen. Click. Why are you not going full screen?
You were full screen.
It wasn't showing here. Okay. Oh wait, and then it went away. Okay, let me do it again. My connection is just being cranky. Okay, so you can kind of see some of these lines in here where I had a little bit of overlap.
That's cool.
And there's like kind of a limited amount that you can do with that. Whereas with ink marker, or with alcohol markers, these also had some amount of overlap, but you can see like there's not like a substantial amount of there's not really a whole lot of line. I did weird here with his face, and it kind of started bleeding out, which was problematic. But they're really neat. I like them. And this brand is great. There's an artist with a YouTube channel called Jazza guy, and he has done a number of kind of brackets with markers, with art markers. And he did one with like all of the alcohol art markers that he could get his hands on. And it kind of came down to like these and Copic markers, which if anybody's not aware, Copic markers are like the professional, great, really expensive markers. These way less expensive by like a lot less expensive. And honestly, price wound up being the biggest thing that took Copic markers over these. No, sorry. Take that back.
Took those over Copic.
Scratch that. Reverse it. It was okay. No, these didn't win. The Copic markers won. But it was because color. There's more Copic colors than there are Ohuhu colors. So he went with Copic. Of course he's gonna go with Copic. He is like extremely biased to Copic, but to be fair, they are really, 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 really good. These are so much cheaper though, and they're really freaking good.
These are also good. Alcohol.
Yes, these are extremely good. These
Nice.
I love that it's just like a big just mass of them. Like when we go into Blix and go to the really nice marker section, it's like, oh, here's $4 per marker. You'll buy this one and then maybe this one, and that's all I can afford.
No, that's like roughly the cost of these guys.
Yeah.
They're it's not cheap, you know. You can get but yeah, this whole pack was like $30.
Nice.
That's awesome.
Crayola really cheap art markers actually did really well. They got far in the bracket. Yeah. Anyway, I'll stop talking about art markers.
Yeah, so add a link to that. Add a link to that in the agenda.
Yeah.
Cool.
What Todd, what is your thanks for existing?
Okay, it's hilarious. I'm going to share my screen real quick so I can show you. And it is this accessory and game for the Nintendo Switch called Ring Fit. And it's two devices, really just sort of a static device. One, it's a leg strap that you put one of the controllers in, and it's then a strain gauge sensor that you plug the other controller into, and then the game can detect your movement through space, and it can detect how much you push and pull in this ring. And the game itself is both a sort of linear narrative game where you do all these little exercises to complete the quests. But there's also got just a bunch of exercises you can do. But we've had this since Christmas. It was a Christmas present for the house, and I just started using it, trying to use it every day, and it's actually kind of fun, and it actually works you out. We're surprised. I thought it was going to be a gimmick, but because the gyro accelerometers in the Switch controllers are so good, and because this strain gauge and the whatever carbon fiber that the ring is made out of is actually a good resistance trainer, I was actually sore after the several times I've used it. So it's, thumbs up for this crazy, yet another crazy add-on that Nintendo makes for their game products. This actually seems to actually work. So that's my crazy thing that I've been enjoying this last week. And Barb froze.
Oh, Barb did freeze.
Well, hopefully her internet will come back once we wave the magic incantation.
Yeah, fascinating. I guess I'll keep going. My thanks for existing. Unfortunately, I can't do the screen share for it. I ducked away for a second to actually grab the Ring Fit, but Todd, you seem to like it so much that you've squirreled it away somewhere. I can't find it.
No, sorry.
I was trying to load things.
Dope.
Load things. Still frozen.
Still no Barb.
Still no Barb. But if she's sort of there, oh, there we go. Oh, excellent. So my thanks for existing is the Swift programming language, actually, and more specifically the Swift team. It's an open source programming language, and I've been watching some of the videos done by that team. You'll notice that like resource number 1, diversity in Swift, they like lead with that. They really do seem to care about the community quite a bit, and they're doing an amazing job. And so I watched this video, What's New in Swift, and they've like keep working on it every year, and they're very responsive to what the community asks for in terms of implementing different things, making it easy to use for programmers and other people in the community. There's just ton new, and just a couple of examples of some of the things that they're doing is if you, they have this algorithms and collections package that they have open sourced. And so you can see it on GitHub. And then you can go look up one of the algorithms, and they give you a little tutorial that they've written. And also you can go see the source. And in the source, it's not just the source. Notice the Apache license, which is very
We're not seeing the screen you're looking at, Carlin, because you just shared like I think one screen or something.
Oh, interesting. So that opened it in a new window. Here, let me. Thank you. Load this tab. So in the GitHub repo, they have the GitHub repository. You can go to Swift algorithms, and then you can click through to an example of one, and they have a tutorial written with example code of how to use it. And so if you've been using Swift but not looking at the GitHub for Swift, I also recommend that. You're using the Apache license for all this. But then they comment out like up the wazoo. All these different algorithms. So it's almost, you can learn about, look at this fancy comment, such a pretty fancy comment. Look at that. So there's just like a lot of things that I really appreciate. And if you notice all these comments with a three bar comment is actually something that is part of the new and also open sourced. Is this the one? Nope. More document compiler that they have released, which is pretty cool to make it really easy to have for people to be able to again open the window. It's here for people to write and share. That's not what I.
Oh well.
Not what I pasted. That's really weird. Oh, I lost it. Anyway, so Swift is doing a really good job. Their document compiler, doc-C that they're calling it, is really a great way to make sure that your code is usable by other people. They like promoting diversity. They're promoting the documentation. They're open sourcing everything. When you watch them in the WWDC videos, they just seem like really nice people. And overall, so yeah, go Swift team, like working your ass off to sort of make that be a positive community. And so
yeah, after seeing like just again and again these various tech and dev communities have these really toxic elements, to have this one community that seems very positive and you know, also doing good like technical work, just like oh man, there is light at the end of the tunnel.
Fingers crossed. Yeah, never go to the dog food factory. But it's from the distance. Thank you to the Swift team for doing such a tremendous job, and the Swift UI team. Yeah, this method's interesting. WWDC week. Go watch the videos.
Yep. That was this week.
Yeah.
It's free to watch.
Yeah.
All right. So ready to start your schematic engines?
Yes.
All right. I guess make my screen share big, Barb, and then I will chat at you while you guys build the circuit that we talked about last week.
Sounds great.
Or did I already talk about this last week? I forget.
No, our cat was dying last week, Tom.
Sorry, I meant like the last transmission we did.
Last transmission we did not. You did not get to do this yet.
Okay, great. So Barb says she's frozen. Can you click share my screen, Barb? No. All the technology's dead. All right, I'll do a song and dance. So op amps are triangles.
Love it.
They have a plus and a minus.
I like this intuitive
output. And when the plus and minus are plus, the output goes this way. When the plus and minus are negative, the output goes that way.
I think you stop being so funny, Todd, because then Barb's just gonna like leave it this way because this is pretty good.
No. All right, maybe I'll just point my other camera at my screen. Uh-oh, Barb's gone.
God.
Unfortunately, Barb's the DM of our show, so she's the one who's in charge of all the stuff. So here, I will instead point my camera at... Will this actually work? This will be hilarious if it works. No, it's not going to work.
All right.
Oh, well.
Okay, well, I've got an op amp on my screen.
Yeah.
All right.
Oh, is she back? Hey! Awesome. All right. Barb's computer's having a conniption.
Really? Seriously? Oh my gosh.
Yeah, I've had so many problems with I'll just open my computer to do this one thing, and then it just decides to go off and wait, I gotta do this other thing. Computer, just do the thing I asked you to do. Stop thinking around.
Yeah, seriously.
All right, so this week, so the last time we all gathered, we talked about and made projects using what's called a astable multivibrator, which is a circuit that's got two elements that kind of go blink, 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 blink. They use two capacitors and they charge and discharge each of those capacitors to make a little oscillator. This is another kind of oscillator, but it uses a different kind of circuit element. It uses what's called an op amp. And if you were to look at what's inside an op amp, it's actually a quite complex circuit. There's actually a bit of a simplified diagram of what an op amp is, and we almost have enough circuit analysis experience from our last several deep fried neurons to analyze this circuit. But the cool thing about op amps is you don't need to know any of that. The cool thing about op amps is it's basically just got two terminals for inputs, a plus and a minus, and it's got a single output called output, and then it's got a power supply input, so plus and minus. And that plus and minus are kind of whatever you want it to be. Usually the op amps are driven by, like, say, plus 15 volts, minus 15 volts. And that's kind of challenging for us normal people who just use USB for everything. So the circuits down below are all going to be driven with just 5 volts. And there's some tricks that we'll have to do to make it so that the op amp can deal with that, because it kind of assumes it can ride the plus minus voltage space as freely as possible. And the way the op amp works, like when we look at it from this sort of zoomed out view as just this little triangle spaceship, is that all we have to know is that no current flows into the inputs of the op amp, which is amazing. Like normally when you have a circuit, current's always flowing out of your circuit into something, into another circuit. And so to have a circuit element that is this passive listener on some other thing you've made is kind of magical. Now, in reality, the inputs do have some resistance, like they do draw some current, but it's in the microamps. It's like barely detectable. And if you're down at that level of needing to worry about that level of current, then you're in a whole different regime where you need to actually start to learn, like, you know, actual engineering instead of the sort of like kind of fun hobby engineering that I do. But the other cool thing is that the inputs are this difference. It's basically, it's always subtracting the plus from the minus input and trying to make that input 0. Because what will happen is that the output will be driven to towards the positive or the negative power supply, depending on whether or not those inputs are overall positive or negative. And that means you can sort of, if you feed back a little bit of that output signal to one of the inputs, you can create different kinds of effects. And the most common ones are things like amplifiers and things like this. But even if you don't have that, you can create a little voltage comparator. And so here's a little simple op amp in a simulator that's just acting as a 6-volt detector. Like maybe you want to have a 6-volt detector. Like maybe you got a 6-volt battery. You want to make sure that it always stays at or above 6 volts. This thing will output a plus voltage, which is like in this case, because I'm driving the op amp with plus 15 and minus 15 volts. This will output plus 15 volts when it's a 6-volt or higher voltage, and it'll output negative 15 volts when it's lower than that. And you actually see this circuit in a bunch of like real products, just using the op amp sort of what's called open loop, where you're not feeding back the output to the input. But the magic starts to happen when you now start feeding the output back into the input. And here's what a sort of basic oscillator using an op amp looks like. And there's two little sub-circuits we've looked at before. There's this one on the top and this one on the bottom. The one on the bottom is just a voltage divider, and it's just looking at 1/2 the voltage of whatever on the output. So if the output is 10 volts, the point right here is 5 volts. If it's negative 15 volts, then this point here will be negative 7.5 volts. And then this thing is just a little RC circuit, like we've done. I think our first deep fried neurons circuit thing was just charging up a capacitor and then discharging a capacitor, except that we're looking at, with this line coming to the negative input of the op amp, we're looking at the charge, the voltage value of the capacitor. We're sort of snooping on it. This is one of the cool things about the op amp, is we can actually look at the charge of the capacitor without really impacting how that capacitor is being charged. And so if you're like, there's a whole paragraph here on the blog on how this works, but basically the output will sort of turn this RC circuit high, start to charge the capacitor until it gets to a certain value, which is dictated by this voltage divider, and then it'll flip state, and it'll go to the negative voltage power supply, and then it'll just kind of flip back and forth, flip, flip, flip. And here's a little movie using a simulator. You can sort of see how it's flipping back and forth. And this is purely using that sort of fun magic of the op amp, where if the differences between the two inputs is positive, it goes positive. If the difference is negative, it goes negative. Right, the other way around. I may have misspoke there. But this is the core of how a lot of op amp circuits work, is you have some sort of reference on one of the pins, and you have feedback from the output to one of the other pins, one of the other inputs of the op amp. And there's literally things called op amp cookbooks that give you variations on this on a theme, and you can do so many things with it. And I should have listed in this a couple of different other simple ones, because there's one really useful one that you can get from this, which is just a simple mixer, like an audio mixer. You know, you want to have a little 4-channel audio mixer, you can make one with an op amp and 5 resistors. That's all you need. So let's say we want to make this oscillator work. Like, you notice there's no discussion of voltage here, because there's, in the simulator, it's kind of hidden that it's at plus 15 and minus 15 volts is what the op amp is using. And so if we want to use this at 5 volts, what do we do? Well, we have to introduce this concept of a virtual ground. And that's what this little circuit element on the left here is. Just yet another voltage divider. This is kind of the thing you always use in circuit design, is just always making voltage dividers of various kinds. And this circuit and the one I just showed, is actually the same circuit, just redrawn, where the sort of assumed ground that's inside the op amp and the definite, like, explicit grounds here on the end of the circuit are shown. Oh, I didn't show it here though. Oops, I showed it here. And so this is the exact same circuit redrawn to use this virtual ground concept, where instead of these things going to ground, they go to this little fake place that's at halfway between ground and 5 volts. So this point is 2.5 volts. This point is 2.5 volts. So it's this 2.5 volts is now what the op amp is going to think of as ground. And here's that same circuit now redrawn in Fritzing, where I've color coded the different circuit elements that I've been talking about. This thing up the top is this RC timer, this RC circuit. And instead of just having a fixed resistor, I've got a little potentiometer hooked up as a variable resistor. And that way you can change the timing of the RC circuit. We've done this before, so this isn't a very new thing. Over here is this little voltage divider comparator that goes in that lets the op amp know what when the voltage that's on the capacitor is half of what the output is. And then here's our other little voltage divider that is providing this virtual ground. And then there's a couple other extra capacitors here.
So wait, is that as I'm doing this, is that virtual voltage divider, or is this that voltage divider?
It's your screen's tiny for me, so I can't see it. But but so if the resistors are going, if the two resistors are going between power and ground, then that's the virtual ground.
Got it. This is my virtual ground.
Correct. Yeah.
Got it.
Yep.
Thank you.
Yep. Yeah, and so if you ever take apart some little audio device, like maybe a little portable Bluetooth speaker, if you take it apart or something, you'll invariably find that the circuit will have this little virtual ground concept in it somewhere, because everything assuming it's not doing the creating a negative voltage. Like some of these have negative voltage creation. Like here's a if you're doing modular synthesizers, here's a little board that does plus and minus 12 volts for modular synthesizers, and then they can have a little analog circuit, same sort of thing. Because there's these little voltage regulator chips you can get that will give you that will give you negative 12 volts and positive 12 volts if you give it an AC signal. So this is an AC, like a 12 volt AC wall wart input, and then from here, this is it can create 5 volts, it can create plus 12 volts, and create negative 12 volts. And that's pretty handy. You can buy this on Tindy from a friend of mine, but it's pretty big. And if we can get away with not needing to create and run a bunch of different voltages, let's do that, because we're just doing pretty simple circuits here. So it's like if we start doing actual cool things that we want to have exact pitch correctness and stuff, then we'll start to use that kind of stuff. But put me back on the screen share, please.
Sure.
Thanks. Yeah, poor Barb. She has to both DM the video and also build her circuit.
Well, if I can't build my circuit, I have 2 already, because I did them earlier to see if I could actually do it, and I did. Wow. Sorry, continue.
Uh-oh, we've got comments.
Yeah, I was just gonna say there's comments, and
it's weird. I don't see comments on my Twitch.
You don't?
I mean, reload. Let's see if
it's on YouTube, because we're streaming to both that and YouTube. Do you see the comments on the StreamYard?
Fascinating. I do see the comments on StreamYard. Yeah.
You can see comments from either Twitch or YouTube on StreamYard.
Gotcha.
Otherwise, you have to go to have.
Gotcha. Oh, that's right. This is our first time streaming on YouTube. Hello, YouTube friends.
Hi, YouTube.
Hello, YouTube.
Hello.
So Rael asks or states that he thought op amps regulate and smooth AC. They can do that. But they're often used to to amplify signals. Like they're called op amps, are short for operational amplifier, because when they were originally created, they were used to do math functions, because as you can see with a plus and minus input, and the fact that they essentially multiply the inputs to an output, that you've kind of got the 4 basic math functions right there. You've got plus, minus, multiply, and divide. And so by hooking up different resistors in the feedback network, you can kind of do almost any math you want with an op amp on a signal, which is kind of weird, especially when you start talking about multiple op amps all hooked up together and you're solving a linear equation just with voltages.
Oh, I love it. Pretty please, my dear. Yeah. Sally with voltages. That's fun.
Yeah, so you could program in a sort of a physics simulator for calculating like how a projectile's trajectory will go, and then have a bunch of knobs that will let you set things like initial velocity, wind speed, air density, or whatever. And it'll have it all be just knobs in the feedback network of your op amp circuit, and then it would output some other voltage that would be how far the projectile could go.
Oh, that's the circuit we should be building. I'm gonna build that circuit.
Sorry, if you're talking to me, you're gonna get things that make bloops and bleeps.
Beep, 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 boop, boop.
Okay, what am I doing?
All right, so the last little bit of this drawing here with the pretty colors is that there's a little capacitor and then a speaker, and the capacitor is to remove that virtual ground that we've created. So the speaker that sees basically just ground can see a signal that kind of deviates around ground, because the speaker works by pushing and pulling air, and so it needs actually a signal that goes a little negative.
Oh, nice.
But now the problem with this circuit is that while op amps are very strong, they're not strong enough to drive a speaker, because speakers are pretty hard things to drive. Fortunately, and here's the breadboard layout. If anyone watching would like to build one of your own, you can go to this blog post and just kind of lay things out as in this breadboard. And Barb and Carlin have seen this layout already, so that's what they've been working on for the last several minutes. And if you only have a single op amp, this particular layout is for a dual op amp chip, because many op amps come in dual or quad packages, where there's actually 2 op amps in this one little black chip. And that's pretty cool, because a lot of circuits are actually just multiple op amps. For instance, if you were to go down the path of making a proper voltage controlled oscillator, or VCO, for a synthesizer, one of the first examples that they give you in the data sheet for one of these dual op amps is, oh look, here's a voltage controlled oscillator using 2 op amps, basically using both op amps of this part. And the really neat thing about this circuit for us is that we see it's basically the same circuit that we've been talking about. It's like, oh, there's this RC circuit. It's laid out slightly differently because of how they're doing stuff. But oh, look, here's this voltage divider network. And there's this weird other feedback element with this transistor, which I haven't done the circuit analysis, so I don't fully understand it. But the cool thing about this is that you've got this input on the left that is a voltage, and it's volts per hertz, I think. So if you were to give it like 1 volt, it would be at 1 frequency. If you give it 2 volts, it would be double that frequency. And then it's got 2 different kinds of outputs. It's got a square wave output and a sawtooth wave output. And that's pretty cool. Just it's like 1 chip, and was it 5 resistors, a couple, like a capacitor and a transistor, and you've got a VCO. So I'm actually kind of wondering if I'd like to maybe try to build this just to see what it sounds like, because I've got a bunch of VCOs in my synthesizer set up. It'd be neat to see how this sounds. But yeah, but we're trying to drive little speakers. So what do we do? Well, since our output is just a square wave, and since we don't care that much about quality, we can do what it sounds like Carlin just got, was we can add a simple transistor amplifier. And this is set up as a current amplifier, where basically we're just turning the transistor as much on as we can, and we're letting all the current flow through the transistor and flow through the speaker. So as the op amp is going high and low, high and low. The transistor is turning on and off, and it's basically connecting the 5 volts to the speaker and then disconnecting it, connecting it, and disconnecting it. And that makes the speaker go wah, 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 and makes the screechy noise that we've been hearing. Mm-hmm. And so if you were to do something with a not just single-sided, not just 5 volts, then this is one half of what's called a push-pull amplifier, where you have another transistor hooked up just down here, but it's a PNP, sort of like mirror image down below. And so the one transistor would deal with all the positive voltages, and the other invisible transistor, in this case, PNP transistor, would deal with all the negative voltages. And that's why it's called push-pull, because it's like one is pushing the voltage up and one's pulling the voltage down.
So where would the PNP be?
It would be. Let me see if I can. I see if this will work. It would be. Oh dear. No.
You're trying to change the screen thing there, Todd?
I'm just wondering if I just put it on the. Yeah, it won't work if I just put it on there, will it?
on where?
Like, oops. Yeah. Oh crap! What just happened? Oh man, my screen's freaking out.
Oh no, me and my asking not use the
Wow, my screen's really freaking out right now. Let me stop screen share because something odd is happening. What is going on? Oh my goodness. My screen is flickering in this really weird way. It's giving me epilepsy.
Oh dear.
Don't have that.
Yeah, if I struck out. Oh, wait, okay, kind of.
No.
What's this weird?
Not allowed.
What is going on? Let me disconnect. I'll be right back.
Okay. In the meantime, we'll just show what we've got. What did you got yours working, right?
I got mine working. I just pulled it apart though because I didn't have the amplifier on it. Mm-hmm. And I the code for is 103 is
for the this guy. I think it's 104.
It's 104. Okay, so that's part of what I thought. Maybe I'd gotten it wrong. I always put those around because I always think of things in microfarads, and then when
mine says 104. All right. I mean, it's hard to read, but
that's sort of an interesting thing. So mine, here, I'll put this back. Yeah. And we'll be able to hear that mine at the, oops, will we be able to hear? Will it go back? We have lost Todd, and I know, do we have it? Yeah, so mine, super pitchy. And then when I replace the capacitor, so this was 103, and when I replace it with a 104, let's see. So that was from pin there to there.
Or no, not, I don't know which pin it is.
Yeah.
The second one on the bottom.
There we go. Let's see if this is a different noise now. Yeah, so it's a little deeper.
Yeah, sounds better.
Yeah, so more capacitance.
Todd's back.
And if I want to make it even deeper, I bet I could take my 103.
Even deeper.
Even deeper. I don't even have room on the board to make it deeper. But here we go. Let's shove in another capacitor in parallel and see what happens. Yeah, so when you put another capacitor in parallel, you get a little lower, little juicier.
Carlin's experimenting.
Yeah, Now my screen's still flickering strangely, but I don't. It's enough that it's not going to kill me anymore. So I don't know what's going on.
Try not to die.
Yeah, I would prefer that.
Make every effort.
Wait, I'm dying. Oh wait, no, maybe not.
No,
maybe not.
No.
Am I dying yet?
No.
Not allowed. Not allowed.
All right.
Here's a question.
Yeah. I wish it was an analog monitor. I don't know what it's a HDMI monitor. I don't know where this flickering is coming from. I've rebooted the monitor and the little dock thing I have that deals with it. It's very strange.
Okay, from here to nope. There.
Let's see if I can get my system showing a screen.
To here. Okay. Yeah, let's get a screen. And where did let's go? Oh, that's great.
EBC.
You're sharing a screen that I don't have to worry about changing. I like it.
Yep.
See.
Oh, helps if I plug it into the power.
There's that. Ooh. It's making farting noises.
Fart.
A speaker doesn't actually, since it's just a coil, doesn't actually care which one is black and which one is red, right?
That is correct.
Did I get this right? Did I get it right? Wait, let's see. I'm gonna chuck this guy in because I think it wants to be there.
I think both sides of my board ground.
This is basically a little staple. Now I kind of want to try using staples on a breadboard. Because
actually, I have some on mine. yeah.
Like, that looks like a tiny staple.
Mm-hmm.
I'm just gonna use a staple and see how that goes. Actually,
I use a lot of old component leads as little jumpers for things like ground and stuff.
Mm-hmm.
Just for that very reason.
Okay, I'm gonna try this.
Load in my speaker.
Oh, maybe. I mean, I doubt it, but
there's no current limiter on the collector.
Yeah, it should be fine.
Here.
Okay.
the speaker has a kind of resistance. It's got 8 ohms of.
Woo! No, I want to go down. Yay!
Oh, we got the LDR going, huh?
Oh yeah.
Nice.
It's very high though.
Yeah.
Yeah, I think maybe the 103 is a better choice than the 104.
Should be higher resistances should be better.
Oh, I was talking about the
yeah.
I was talking about the capacitor.
Oh, sorry. Yes.
Yeah.
Yes. A 104 is the minimum, I believe, was what you'd want.
Yeah, that's what I've got right now. I've got a 104, but Carlin was trying 103 and 104.
No, it's deeper.
Oh, gotcha. Yeah. Yeah, you could even do a 1 microfarad, and then you'd get almost an LFO, which I've got a demo of as an idea for what you could do later.
Ooh, let's see it. Let's see it.
I want to see.
So okay, on this board, I have two op-amp oscillators. Basically, it's the exact same circuit cloned, and so over on the left side, I have our oscillator, and This is a. Let me turn this off for a moment. So this is what the fancy kids call a Vactrol. This piece of heat shrink and electrical tape. If you take a light sensitive resistor, an LDR photocell, and you put an LED like this, and then you heat shrink them together or wrap electrical tape around them, then you have what's called a Vactrol. You could also call this a opto-isolator. But this is sort of the hack synthesis, the DIY synthesis way of doing it. And there's some very famous synthesizers from the 70s that use this technique, but I think they used incandescent lights instead of like those little wheat-shaped bulbs that existed back then. And so you could buy these now in the synth market, where they will have these two things heat shrink together, and you treat it as one component. And so that's what this is. Unfortunately, I didn't do the sealing of it very well, so as I wave my hands over it and block the light, it still is responding to light. So it should not respond to light. And then over here, I have a much slower oscillator. This one is currently oscillating at 4 hertz, and the output of it looks like this. Wait for it to stabilize here. So that's a square wave output, and we can. Oh, I think he turned off. We can lower its frequency or raise its frequency up, and now it is at. Oh, it's too fast. Like
capacitors.
Like 100 hertz or so. And so what we can do is we can feed this into our other circuit and use it as essentially a modulator for this one.
Ooh.
Oh, nice.
That's so cool.
And the cool thing is that since this is sort of an op-amp circuit and we can like sort of probe different parts of the voltages, I can look at, instead of the normal output that's just going high-low, I can look at the capacitor charge and discharge thing and feed that in instead. And that's what this part that's what it sounds like. Nope, that's not right. What am I doing wrong?
That's what I had right there.
Nope. Nope. Oh well. For some reason I have a miswiring here, so I won't be able to show that to you. But I can show the normal output again.
Awesome.
And if we add instead a much bigger capacitor, this is a 1, here's the 15.
Ooh. Yeah. Oh. Yes. So cool. That's so exciting.
So anyway.
Yeah.
That was fun.
Yeah. So it's one of the fun things about this is that you can get into the realm of where you're starting, like, oh, I'm playing 2 tones back and forth, but if I play them fast enough, it starts to sound like a 3rd tone, which is pretty cool.
It is pretty cool.
Nice.
All right, so it is 6:28.
6:28. Yeah, we got to wrap up in a minute here.
Cut off at 6:30. So I think sorry for the long explanation. And
no, that was great. Thank you.
That was super cool. Yeah. Thanks.
For our upcoming switch cameras.
Oh.
I was trying another one, but it wasn't working, so I'm back to my 104.
Nope, wrong camera.
I'll play with it more.
There we go.
There we go.
All right, so I know that Barbara's already had this circuit working at least 2 other times using 2 different chips. So you get a pass this time, Barb.
Yes.
And so I think for our next week, we're supposed to try to make something creative, an actual artistic expression using this basic circuit. I have no idea what I'm going to do, but using light-sensitive resistors, using switching in and out different capacitors or different resistors, you can get different tones. You can even make a little keyboard that way. These are some ideas that I've done in the past. So maybe something like that would be applicable. Other than that, I don't know what we're going to do.
And on that note,
yeah, we'll see. It'll be great.
Woohoo!
Thank you all.
Thank you for Todd for showing us the stuffs.
It was great.
Op amps are fun.
Woohoo!
Cool. All right.
Universe.
See y'all next week. Cheers.
Cheers.